Hey guys, welcome back to another New Horizon Tutoring ACT Math video. Today basically we're just going to be working on what are called exponents. I'm pretty sure you guys have heard of them before, worked with them a little bit, maybe depending on where you're at. So yeah, if you want to think back to last week, we were dealing with log, which I would say is probably the more complicated of the two, just because, at least the way that I learned it, and I feel like the way that most people learn about it, you learn about exponents first and then you deal with log, because log is kind of like a branch off of exponents, I suppose, if you can think about it that way, or it's just like very closely related to exponents. So obviously today what we're learning is definitely going to help you with log, which is great because log can be kind of confusing sometimes if you haven't worked with it a lot, but it's really just one of those things where you have to work with it more and more, just start to incorporate some of the modes of thinking into how you assess problems, stuff like that. So yeah, that's what we're going to be doing today. It's going to be a pretty similar setup, meaning that we'll just go over notes. So I'll go through like the very basics of exponents, just like I did with log, and then we'll go over some problems. And we didn't have too much time last week to deal with log problems, so if we do have any time at the end of this video, we'll go over that. If not, I can always incorporate it into like the beginning of the next video, if you guys think that's necessary. So yeah, we're just gonna go ahead and get started. Like I said, starting out with notes, moving on to practice, and then seeing what we have time for at the end. Okay, so this is kind of our working definition, I guess, of like what exponents do, what they're used for. So it just says that exponents are used to multiply the base by itself, however many times the exponent denotes. So obviously there's a couple key terms in there that I'm gonna highlight and define a little bit more clearly what we mean by that. So we have this word, the base here, and also exponent. So what exactly do we mean by those two terms, and how is that going to look in an actual problem setting? So I'm just going to use these variables to deal with it, because once we get to the rules within the math packet, these are kind of the variables that we work with, and I forgot to mention it, but it's the same exact page as log, which is kind of nice. It's going to be page 10 like I wrote up there out of your math packet. So I would definitely recommend having that with you today. Yeah, it's like a pretty similar setup to the log portion of page 10. It doesn't really give like kind of basic information, which is what we're going over right now, but it does list out the rules very clearly and nicely. So we are going to go over those rules in a second once I kind of get this intro stuff out of the way. So yeah, back to what I was saying before, we have two different terms that we need to talk about, our base and our exponent. So this value down here, whatever it's going to be, a lot of times it is going to be a variable, a lot of times it's going to be a number, just depends on the specific problem. Whatever it is, that's what we call our base, and this value up here is going to be the exponent portion of it. So yeah, that's really not too difficult. We have our base, we have our exponent, and just for the sake of showing us, now I'm going to translate it kind of into numbers, I guess, instead of dealing with variables, just so I can show you guys exactly what I'm talking about when I say that we're multiplying the base by itself, however many times the exponent denotes. And once I write it out, it should be relatively straightforward and clear, but sometimes it's just a matter of remembering instead of kind of like getting the habit switched, just because if you don't deal with exponents a lot, or kind of like if you're rushing through a problem, it can be difficult to maintain that mindset, if that makes sense. Okay, so let's say, for example, I have the exponent term 2 to the third. So there's really one other way that I could write that out, and that would be this, where I'm multiplying the base 2 by itself however many times the exponent denotes. So obviously we have 2 to the third here, so I'm multiplying 2 by itself 3 times. Pretty self-explanatory. What is incorrect and will never be correct in dealing with exponents, sometimes, like I said before, if people haven't worked with exponents a lot, or if they're just like rushing through a problem, they'll multiply the base by the exponent, which is not correct. Because if we multiply this out, we get 8, which is the correct answer, right? But if we multiply this out, we get 6, which are obviously 2 very different numbers. So that's kind of just like a mathematical fallacy, or kind of just like a trick that people fall into. So it might be kind of obvious to see that here, but just make sure that you're mindful of that when you go into answering problems, especially multiple choice questions. Because sometimes it can be a little bit harder to see if you're just like working off of the answer choices. It's a little bit easier for people to like visualize, I guess, that it's 2 times 3, which again is incorrect, than it is for them to like multiply the whole thing out. So just keep that in mind, and you will, as you work with exponents more, just start to be able to do this stuff mentally, which is really nice. You'll just see 2 to the third power and automatically be, oh, okay, that's 8. Depending on like if the numbers are small enough for you to work with them. Obviously, if it's like 6 to the 4th, I don't know that off the top of my head. It just kind of depends, like I said. Okay, so that kind of is the basics of exponents. I have a couple more things that I'm going to talk about before I move on to the rules. So we're going to go ahead and do that now. Okay, so this again is just a little bit of background info dealing with the rules. So the rules of exponents are basically used to both simplify expressions with exponents in them and eventually solve equations with exponents in them. So obviously you can like have the rules in front of you right now, but I'm gonna go a little bit more in depth and kind of like explain each of them. And it kind of is something that you are gonna have to memorize, like the rules, but they all logically make sense, at least I think they do for the most part. So if you understand the concept behind it and are able to like reason about it, I think it makes it a little bit easier to memorize it and then to just like apply it to problems in general. Okay, so there's one more other thing that I want to talk about before I get into the actual rules themselves, and that is the concept of square roots. So essentially, square roots are going to be the opposite, or I put square in parentheses just because that's like, I'll explain that in a second, but taking the root of something is the opposite of taking that exponent of the same base, dealing like with the same numbers and stuff. So again, opposite operations, it's kind of like multiplication and division, addition, subtraction, stuff like that. So yeah, square root is, I would say, like the most common root, and it's just written like, let's say that, like square root of x. Sometimes you'll see a little like superscript 2 right there. It's the same exact thing, and that is going to be the opposite really of x squared. Or let's say, for example, another really common root to use is the cube root. So we have superscript 3 there. When you're dealing with anything other than square roots, you do need to make sure that you specify that superscript there. Like I said, for square roots, you technically don't have to, but if you're dealing with any other root, you do have to have whatever root you're taking there. And that's going to be the opposite of x cubed. Same thing if you want to take the fourth root of something, that's really the opposite operation of x to the fourth. So really, if I were to take the square root of x squared, that cancels out and leaves me with x. Or same thing, if I take the cubed root of x cubed, cancels out and gets x, which is what I mean by like the opposite. If you're dealing with like an exponent like this, and let's say that you get everything to one side of the equation and you're left with x squared, but it's asking you for x, you really just have to take the square root of both sides. Or if you're left with x cubed, again, take the cube root of both sides as you would to solve an equation. Okay, I think that's basically all of the kind of like prologue-ish I want to do about this. So now we're just going to move into the rules and the explanations behind them. Okay, so this is the first one. Obviously deals with multiplication and addition, kind of. So here we have a to the power of m times a to the power of n is equal to a to the power of m plus n. So one key thing to notice about this is the bases are the same. You can only apply these specific rules that we're dealing with, a through f. Well, I guess some of them don't necessarily deal with like two of the same bases, but the ones that do deal with like, I guess it'd be both a and b, the ones that do deal with like two different values, the base does have to be the same in order to apply these rules. So definitely keep that in mind. I'll show you what you cannot do. Let's say we have a to the power of m times b to the power of n. You can't say ab to the power of mn, really. Or you can't do it like that. It just doesn't work. So that is incorrect. Really, the most concise way that you would be able to write that is just am times bn. Because the bases are different, you can't combine those two separate exponents. Just keep that in mind. Okay, so another thing that I kind of want to talk about with this specific one, and it applies directly to B as well, so keep this in mind when we go over B. It can be kind of confusing to kids, I guess, because they see that we're multiplying these two terms here, so they assume that you should multiply the exponents. But it's kind of just something that you have to accept that that's not the case. Whenever you're multiplying two terms with the same base with exponents, you have to add the exponents. So the way that I see it is if you're dealing with exponents and you're like doing an operation between the two, like we are here, you kind of do one step down in dealing with their exponents. So I think about it as like addition is like the little brother of multiplication, right? Because it's not like as, I don't want to say effective or like strong, but kind of. Like 2 times 3 is 6, obviously, but 2 plus 3 is 5. So it's like, it doesn't increase as much if you add something compared to if you multiply it, obviously, like, duh. So just think about like that kind of relationship. Make sure that you're not multiplying these exponents, you are in fact adding them when the two individual terms themselves are being multiplied. Okay, so rule number B, it's essentially the same line of logic where we have two different values here. Same base, still, that same rule applies, but now they're being divided by each other, right? So instead of dividing the exponents themselves by each other, we're gonna take the little brother operation of division, which is subtraction. So we're gonna subtract the exponents from each other. So yeah, it really is just kind of the same logic. One thing that I do wanna point out, I'll just give an example right here, and this can really relate to either A or B. I'll just deal it with A. Let's say we have like x cubed times x. Obviously, we're dealing with that rule up there, right? Technically, whenever there's not like another numerical exponent assigned to a value, it's really gonna be 1. Same thing goes for like coefficients, right? Like let's say we just have x compared to 2x. The coefficient of 2x is gonna be 2, right? Technically, even though 1 doesn't have like a very apparent coefficient, even though x doesn't have a very apparent coefficient, it still has that 1 there. We just don't write it because it's redundant and we don't need to. So yeah, same exact line of thinking for coefficients goes for exponents. So if you're new to this, I would recommend, if you see something like that, writing the 1, because that'll kind of instill, okay, like I have to add 3 and 1, because sometimes what people do is if they don't see that, they just say, oh, there's nothing there I have to add, it's gonna be x to the 3rd, which is incorrect, right? Because we do have an exponent here, it's just not written out. So then in that case, it's gonna be x to the 4th, obviously. Okay, awesome. Okay, so C is kind of closely related to A and B in the fact that we're taking the little brother operation, really. This time it's just dealing like with one value here, right? We don't have two separate A values. So we have A to the power of M, and then that value itself is being taken to the power of N. So instead of taking the exponent M to the power of N, we multiply those two individual exponents, because same line of thinking from multiplication to addition is exponents to multiplication. So it's really just kind of like one step up. But like I said, it's the same exact like line of thinking. So yeah, just make sure you kind of remember that. Like I said, those are all pretty interrelated into like the way that you have to remember those rules. Okay, so this rule kind of diverges from the pattern that we've been dealing with. Now we're dealing with negative exponents, which can get people a little freaked out. But for negative exponents, like the same exact rules up here apply, but there's a couple extra things we have to do, because a lot of times ACT or just like math teachers in general don't want negative exponents, they want all positive exponents. So if we have a negative exponent in our answer, that's a problem, right? We have to solve that. The way that we do is we simply flip the fraction, and then that makes the exponent positive. So even though it doesn't really seem like it, this a to the power of -1 is technically over 1, right? Anything divided by 1 is itself, so logically we can write that. So really all you have to do, like I said, is flip the numerator and the denominator, find its reciprocal, right? That's what it's called. And then that exponent becomes positive, problem solved. The exponent itself stays the same, the base itself stays the same. It's really just dealing like with the sign of that exponent. And these two things are exactly equivalent, it's really just different ways to write them. And this can also work in the opposite way. So let's say, for example, we have 1 over a to the -n. If we want to write that as a positive exponent, what do we do? We're going to flip the numerator and the denominator, right? So now it's just going to be a And since we flipped the numerator and the denominator, this exponent is going to become positive. So now it's a to the power of n, technically over 1, but like I said before, we don't really have to write that out. So yeah, just make sure you keep that in mind when you're dealing with negative exponents. And as always, if you're dealing with like a multiple choice question in ACT, check the answer choices. Most of the time in my experience, yeah, I would say so. Most of the time in my experience, ACT doesn't want negative exponents. So like I said, just keep that in mind. And dealing with like dividing negative exponents and multiplying negative exponents can get kind of tricky, but as long as you maintain like these core values in the rules, it really is not too difficult. If you have to, like write it out to make it a little bit more straightforward. Okay, so this next rule is pretty straightforward. I don't have to do too much explaining with it. Rule E, it tells us that a to the power of 0 is equal to 1. Always. Doesn't matter what a is. Whenever something is taken to the power of 0, it's automatically going to be 1. I know there's like an explanation behind why that is, because like logically you would think it'd be 0, right? Because you're taking a, or whatever this value is, times itself 0 times. So it is kind of weird. You do have to like, I wouldn't say you technically have to like memorize that rule, but just kind of be aware of it. Anything taken to the power of 0 is not 0 as it may seem. It's going to be 1. Okay, so last rule that we're going to deal with is rule F. And this one is really important. It is a little bit trickier, kind of, but it is super important in like solving problems as you get a little bit more complex. So basically what it says, if we have a value a here, taken to the nth root, and that's really how you say that, taken to the nth root, it can also be written as a to the power of 1 over n. So this is kind of what I was talking about, or what I was trying to get at when I brought up square roots before, right? Because obviously square roots are very related to exponents. Like I said before, it's going to be the opposite operation to exponents. So yeah, just keep this in mind, whatever that n value is. So for example, let's say we have like the cube root of a. It can also be written as a to the power of 1 over 3. And then if you like are dealing with this, and if you get a to the power of 1 over 3 into that form, into that exponent form, then it becomes a little bit easier to apply these rules. Like let's say we're multiplying it by another a term with an exponent. I personally think it's a lot easier to do like the quick rewriting from this form into the exponent form, just so that you can more easily see and apply those rules. Even though technically these things are the same exact representation, just written 2 different ways. And then again, vice versa works as well. If we have a to the power of 1 over 4, that can also be written as the 4th root of a. Again, just make sure that you're denoting that correctly with that superscript. Okay, so that basically is it for kind of like the strict note portion of this. So what we're going to go ahead and do now is, like I said before, some practice. So I'm going to start out with exponent practice, just because I kind of gave you guys like some loose examples for log, but I really didn't for exponents because I wanted to have time to get the problems. So we have like roughly 15 minutes, which is perfect. So I really think we'll be able to get through our exponent problems. And then if we have time at the end, we could perhaps revisit log. Some of the log questions are a little bit longer and more complex, just because log is a little bit more complex than exponents, I think. But yeah, we'll kind of just see what we have time for. Okay, so I went ahead and wrote 2 problems up there just because these are relatively simple, pretty straightforward. This first one just says to simplify 3x times the quantity 2x cubed. And problem number 2 tells us to simplify square root of 3 times the square root of 20. So I'll let you guys kind of think about that a little bit and then we'll go over it. Okay, so we're gonna go ahead and go over these. First, dealing with number 1. So 3x in and of itself can't be simplified down any further, but the quantity 2x cubed can be. So we're gonna tackle that first, and then we're gonna multiply it by 3x because that's what's happening here. So like I said, quantity 2x squared, quantity 2x cubed. So whenever I personally am dealing with exponents, I like to take it in 2 different chunks. I guess it depends if you're dealing with both numbers and variables, but those are the 2 different chunks I like to take it in. I like to deal with numbers first and then variables second, just so I don't get confused. So that's what I'm gonna do here. So really another way to write this out is 2 to the power of 3 times x to the power of 3. So one way that you can think about it is that this to the power of 3 exponent is being distributed kind of. And the reason that we're able to distribute that and the reason that that's what we have to do is because of these parentheses. So if I were to write it out, for example, like 2x cubed, the 3 exponent is only being applied to that x, right? It's not being applied to that 2. It's just 2x cubed. But since I put parentheses around it, I'm saying that that whole quantity 2x is being cubed. So like I said before, you can really section it off into 2 different parts, the number 2 and the variable x. So just keep that in mind, that is going to be the case when you're dealing with like exponents, parentheses, stuff like that. Okay, so dealing with the number portion first. If you remember, 2 cubed is just 2 times 2 times 2, right? Multiplying the base by itself however many times the exponent denotes. So 2 times 2 times 2 is going to be 8. So we have 8 for this portion here, and then x cubed, you really can't do anything different with that. So it's just that. And then obviously we still do have to multiply it by 3x. So one check that we have to do is that our bases are the same, right? And by bases, I mean our variable bases. With number bases, you can just simplify it out fully and like take the actual exponent of it and multiply it out, so you're only left with like one core number. But obviously you can't get any simpler for the exponent itself than x cubed. Like you can write it as x times x times x, it's the same thing, but it's just x cubed. So like I did for this portion up here, I'm gonna deal with the numbers first and then the exponents. So we just have 8 times 3, which is gonna be 24. So that's our number portion of it. And then we have x cubed times x, which when I gave you guys like an example of problem A earlier, I did not realize that it was this close to the problem. But it's basically the same thing where, like I said before, this is dealing with rule A. So whenever we're multiplying 2 exponent values and they have the same base, we add their exponents, right? So we have 3 here, technically a 1 there, so we're gonna be left with x to the fourth. So then our final term, combining both our number component and our variable component, is 24x to the fourth. And that's really as far down as we can simplify it. Awesome. Okay, so that's number one. Moving on to number two, it wants us to simplify square root of 3 times the square root of 20. Okay, so even though this isn't like directly dealing with exponents, technically it's still dealing with square roots, which this is just like a super important core skill, being able to simplify down square roots. It's kind of like its own little baby tiny subsection. And then you can also like obviously apply it to problems whenever you're simplifying something, whenever you're solving something out. So it's super important. So really what you have to do is within these number values, you have to look for perfect squares. So if you think about perfect squares, it's like 4, 9, 25, 36, on and on and on. So I know that 3 is not a perfect square, so I'm gonna kind of disregard that as of right now, because the square root of 3 is as far down as I can simplify that, right? But I know that 20 can be factored out into a couple different things, right? We could either factor it as 1 times 20, which isn't helpful, 2 times 10, neither 2 nor 10 are square roots, or perfect squares, so that's not really helpful either, or 4 times 5, which I know that 4 is a perfect square, so that is very helpful. That's really what we have to do. So you can just go ahead and rewrite square root of 20 as square root of 4 times 5. And then one way that like I visualize it when I was first working with like simplifying square roots is just to write it out like this, where you kind of like separate those two, because then I can see, oh, square root of 4, I know that's 2, pretty obviously. And obviously, like if you recognize it just from square root of 20, you don't have to go through these intermediate steps, but that's kind of just like the reasoning behind what we're doing. So yeah, like I said before, I know that the square root of 4 is really just going to be 2, and we can't simplify down the square root of 5 anymore. So it's just the square root of 5. But then obviously we still have that term up there, the square root of 3. So we need to multiply that as well. And then we can really just combine those under the same square root, kind of like the opposite of what we did right here, and like actually multiply those out, because that's going to be the simplest form, right? So then we're just going to be left with 2 times the square root of 15, and that's going to be our simplest answer that we can get to. Awesome. Okay, so I have a couple more questions for exponents, and then we'll see if we get to logs. Just a really quick side note, another reason why simplifying exponents is important, but simplifying square roots and just like roots in general is really important, is because the ACT is almost always going to leave it in this form. They're never actually going to find the square root of 15, because that would multiply out to a number, right? It'd be, what, somewhere in between, it'd be like almost 4, because it's almost the square root of 16, which is 4 flat. But it'd be some infinitely long non-repeating decimal, and that means that we have to round it out, and then it's technically not as precise or accurate as it is just to keep it like that. So whenever you do have to leave the like radical in there or the square root in there, they always want it in the simplest term. So just keep that in mind. And as always, consult your answer choices to see what form they want it in, but I'd say like 95% of the time, they're gonna keep that radical in there. Okay, so another exponent problem, like I said. This one just reads as 9 to the power of 2x plus 1 is equal to 3 to the power of x minus 4, and it wants us to find x. So I'll give you guys a couple seconds to write that down, think about it, and then we'll go over it. Okay, so back to the problem. Really when you're dealing with like a pretty straightforward problem like this, what you need to do is you need to get that base value to be the same. And we'll see why in a second, but basically if you can get that base value, whatever it is, to be the same, then you can essentially like cancel out the bases and take the exponents and set them equal to each other. And then we can find x. So this one is like pretty easy to see since 9 is a perfect square. It can also be represented as 3 squared, right? So I'm really just gonna rewrite this to 3 squared in place of that 9, but it's still taken to the power of 2x plus 1. So now, kind of if you think back to our notes, I believe this was rule C, where we have an exponent taken to an exponent. So whenever that happens, we have to take those two exponents times each other, right? This one might be a little bit more difficult, I guess, just because this exponent is like a polynomial instead of just one value, but really we just have to distribute this 2 out to each term in there. So to simplify that down so that I can solve, I'm just gonna take 2 times 2x, which is gonna be 4x, and 2 times 1, which is just gonna be 2. And so that's how we got from 9 to the power of 2x plus 1 to 3 to the power of 4x plus 2. And then again, that's still being taken equal to 3 to the power of x minus 4. And then like I said before, when you get these two base values to be the same, it's not like they're really canceling out, but what we can do essentially is take the exponents and set them equal to each other instead of having like this whole thing set equal to each other. So now we have 4x plus 2 is equal to x minus 4. Subtract that x over, we get 3x. Subtract that 2 over, we get negative 6. Divide both sides by 3 and we get x is negative 2. And that is going to be our answer. Okay, so I'm going to breeze through another problem super quick just because we have a couple minutes left and I really don't think it'll take us that long. And then we're going to wrap up and call it a day. Okay, so again, we're dealing with an equation where this time, instead of exponents, we have square roots, but it still wants us to find x. So first thing I'm gonna do is move everything that I can onto the opposite side of the side that contains the x. So basically, I'm just gonna subtract this 2 over from both sides so that I'm left with the square root of x minus 3 is equal to 5 minus 2 is 3. So now the reason that I wanted to include this in here is because it's a really good example of showing how exponents and radicals are opposite operations. So now I know I have this operation, the square root, being done to x, so I need to undo it by doing the opposite operation, which, like I said, is going to be the exponent. So since this is a square root, I'm just gonna square both sides. If it was a cube root, I would cube both sides, etc., etc. So then by taking the square of a square root, it essentially just cancels it out. So we're left with x minus 3 is equal to 3 to the power of 2 is going to be 9. Add that 3 over and we're left with x is equal to 12. That's going to be our answer. Awesome. Okay, so we ended right about on time, which is great. So yeah, I would say just make sure you're like still looking over those exponent rules, those log rules. I got all of these practice from the ACT books like I have in the past. So it's a pretty accurate representation, but if you want any more work, basically just like, ideally if you have the ACT 36 book, that's really good because it sections out exactly where in the book it talks about exponents and logs. Or if you have the ACT Math and Science workbook, I believe it's called, that's really good for it too. Okay, awesome. So like I said, we're gonna call it a day and we will see you guys next week.